This is the Unit 2 Exam B solution video for Math 1100. Question 1, this would come from section 3.1, find intervals where the function is increasing or decreasing. For that we need to find the first derivative. So this is a quotient, we're going to use a quotient rule to find y prime. So bottom function multiplied by the derivative of the top function minus the top function multiplied by the derivative of the bottom function divided by the bottom function squared. Now, if we combine some like terms here in the numerator, we're going to have x squared minus 16 minus 2x squared. So that's negative x squared minus 16 over x squared minus 16 squared. So now we find the critical values. Excuse me, remember critical values occur when the first derivative is equal to 0 or when it is undefined. So when we have a quotient like this, it can be undefined when the denominator is equal to 0. That's going to occur when x equals positive or negative 4. And the quotient is going to equal 0 when the numerator is equal to 0. But if we take that expression in the numerator and set it equal to 0, it's going to have no solution. It's going to end up being x squared equals negative 16, and that has no real solution. So the critical numbers are going to come from the values from the denominator that make the denominator equal to 0, which is positive 4 and negative 4. So if you recall, next step after you find the critical values is to plot them on a number line and test some values. I'm going to test negative 5, 0, and positive 5. If I plug negative 5 into the first derivative, negative 5 squared is 25. Multiplied by negative 1 is negative 25 minus 16 is negative. The denominator is always going to be positive because whatever this turns out to be, it's going to be squared, which makes it positive. So we have a negative value divided by a positive value, which is negative. Now when we test 0, 0 squared times negative 1 is 0. 0 minus 16 is negative. Divided by a positive is also negative. And 5 squared times negative 1 is negative. Subtract negative 16, or subtract 16 is still negative. Divided by a positive is negative. Well, you can see here there are no intervals where the function is increasing. All of these minus signs indicate the function decreases everywhere. So the interval of increase would be none. It's decreasing. Now, if we were to graph this function, the original function y equals x over x squared minus 16, there would be a vertical asymptote at negative 4 and 4. So we can't simply state that it's decreasing from negative infinity to positive infinity because negative 4 and 4 are excluded from the domain. So we'd say it's decreasing from negative infinity to negative 4, and then from negative 4 to 4, and finally from 4 to infinity. Okay, question 2 is from 3.2, finding points of relative minima or maxima. The first derivative test, it's very similar to question 1, so we're going to start by finding y prime. So negative 3x squared minus 28x minus 60. And now we're going to set this equal to 0. And solve. Now remember, critical values can occur when the first derivative is equal to 0 or when it's undefined, but this quadratic expression is never undefined. So we're going to factor it. So I'm going to multiply 3 times 60, that's 180. So we have factors of 180 that are going to add to negative 28. So let's take negative 18 and negative 10. That's going to multiply 180, but also add to negative 28. So we'll factor this one by grouping. And if we factor that first grouping there, or group that first grouping rather, we're going to factor out a negative 3x, which will leave x plus 6. And from the second grouping here, we can factor out a negative 10. That's going to leave x plus 6. So the factors are x plus 6 and negative 3x minus 10. So the two critical numbers are x equals negative 6 and x equals 10/3. And that's going to be negative 10/3 rather. So now that we have our two critical numbers, we can place them on a number line. Negative 6 and negative 10/3. So if we choose some test points, like negative 7, negative 5, and 0. So plug negative 7. Negative 7 plus 6, it's negative. Negative 3 times negative 7 is 21 minus 10, it's positive. Negative times positive is negative. Negative 5 plus 6 is positive. Negative 5 times negative 3 is 15. 15 minus 10 is positive. Positive multiplied by positive is positive. 0 plus 6 is positive, but 0 minus 10 is negative. Positive times a negative is negative. So you can see here the function decreases to negative 6, then increases to negative 10/3, and decreases. So negative 6 would represent a relative minimum value. Negative 10/3 represents a relative maximum value. So relative minimum at negative 6, comma, and we got to find the y value, and then there's a relative max at negative 10/3. Now to find the y values for each of these x values, we just plug them back into the original function. So for negative 6, if we plug negative 6 in for all the x, we would get negative 2. If we plug negative 10/3 in for the x values, and if we want to leave that in a fraction, it would be 202 divided by 27. Now, question 3 is also from 3.2. This is slightly different. This is points of absolute minima or maxima over this interval. It begins the same, so we need to find y prime. So that's 3x squared minus 2x. And we need to find the critical numbers. So set it equal to 0, factor out an x. So x equals 0 and x equals 2/3. Now how this is different from the first derivative test, rather than placing those critical numbers on a number line like we did in question 2, we find the corresponding y values for each of these x values and for the two endpoint x value of negative 1 and an x value of 2. So for x equals negative 1, y equals, so when x equals negative 1, we have negative 1 cubed, that's negative 1. Negative 1 squared is 1, so we have negative 1 minus 1, that's negative 2. Negative 2 minus 4 is negative 6. For x equals 0, that's from this critical number, we're going to have 0 minus 4 as negative 4. For x equals 2/3, y is going to equal, if we keep it as a fraction, negative 112 over 27, or about negative 1.1. And then for x equals 2, we're going to have y equals 2 cubed is 8, 2 squared is 4, 8 minus 4 is 4, 4 subtract 4 is 0. So we look now for the highest value and the lowest value, y values. So y equals 0 actually is the highest y value because all the rest are negative. So this is the absolute max. Negative 6 is the lowest y value. So negative 1, negative 6 is the absolute minimum. So this is our minimum, absolute minimum rather. This here is our absolute maximum. Question 4 is from 3.3, finding intervals of concave up or concave down. This is the second derivative. So start with the first derivative, obviously, 4x cubed minus 12x squared plus 10x minus 2. So then the second derivative is 12x squared minus 24x plus 10. Now we're going to set that second derivative equal to 0, and I'm going to factor out also a 2. So now we need to find where this second derivative is either equal to 0 or it could be undefined, but this is a quadratic expression. It's never going to be undefined. So we just need to figure out where it's equal to 0. So 6 times 5 is 30. We need two values that multiply to 30 that add to negative 12. And the problem is there are no two numbers that multiply to 30 that add to negative 12, which means doesn't factor. So unfortunately, or fortunately, I guess it depends on how you look at it, we get to use a quadratic formula where this is A, this is B, this is C. So x equals the opposite of B plus or minus the square root of B squared minus 4 times A times C all over 2 times A. Now we need to figure out this term underneath the square root, that's called the discriminant. And it turns out to be 24. So this is 12 plus or minus the square root of 24 all over 12. Then we need to simplify the square root of 24. That's going to be 2 square roots of 6. So this is 12 plus, let's try that again, 12 plus or minus 2 square roots of 6 all over 12. And then the 12 here and the 2 here and this 12 can all divide by 2. So this is going to be 6 plus or minus the square root of 6 all over 6. Those are the two values from the second derivative that make it equal to 0. So we place those on a number line now. 6 minus root 6 over 6 is the smaller of the two, and then 6 plus root 6 over 6 is the larger of the two. It might be easier to see what those numerical values are. So if we subtract 6 minus the square root of 6, and divide that by 6, we get about 0.6. So this right here is roughly 0.6. So a test value could be 0 over here. Now 6 plus root 6 divided by 6 is 1.4, roughly 1.5. So 1 is in between them, and 2 is over here. So these those are our test values, 0, 1, and 2. So plugging 0 into the second derivative. We have 0 minus 0 plus 5. 5 times 2, that's positive. Plug 1 in as a test point. That's going to be 6 minus 12. That's negative 6. Plus 5 is negative. Times 2 is negative. So this is negative. And then plugging in 2. 2 squared is 4, times 6 is 24. 24 minus 24 is 0 plus 5. Times 2 is positive. So it's concave up from negative infinity to 6 minus root 6 divided by 6, and also from 6 plus root 6 divided by 6 to infinity. So that's concave up intervals. And it's concave down between 6 minus root 6 divided by 6 and 6 plus root 6 divided by 6. Okay, question 5. There's an application of concavity or second derivative from section 3.3 called point of diminishing returns. And it's really nothing more than the inflection point or point of inflection. So when it says find the point of diminishing returns for the function, what it's asking you to do is find the inflection point. Well, the inflection point is from the second derivative, where the second derivative is equal to 0, or where it's undefined and it switches concavity, so either positive negative or negative positive. So what we need to do is find the second derivative of revenue. So first derivative is 3 times negative 2/3 x squared plus 16x. The 3's would cancel, leaving negative 2x squared plus 16x. The second derivative is negative 4x plus 16. Now when we set that equal to 0, we get x is equal to 4. Now this descriptor right here isn't part of the function. This is the revenue function. This is a description of what the domain is. X is the amount spent on advertising in thousands of dollars. So the constraint here is that the number of thousands of dollars spent is from 0 to 8,000. So according to this company only has $8,000, up to $8,000 to spend on advertising. So if x equals 4, it's within that constraint. Now remember, this is not x equals $4. This is 4 in thousands of dollars. So this is $4,000. Now we need to prove that it's an inflection point, which means it has to switch concavity. So if we choose 3 and 5 as test points, in the second derivative, excuse me, negative 4 times 3 is negative 12 plus 6 is positive. If we test 5, negative 4 times 5 is negative 20 plus 16 is negative. So it changes concavity, which means that is an inflection point. So find the point of diminishing returns for the function. So the point, now if we want to read this, I guess in a literal sense, a point of diminishing returns is a point on a graph. But in the context of this problem where R represents revenue and X is the amount spent on advertising, the point of diminishing returns here means what's the point at which the amount spent on revenue starts to bring you decreasing returns. That's the point of diminishing returns. And that's when you have $4,000 spent on advertising. So $4,000 on advertising would be the max you would want to spend after that. You can see it switches to concave down, meaning you have decreasing returns. So $4,000 would be the point of diminishing returns for this revenue function. Okay. So this rancher is going to build rectangular corrals adjacent to each other like this. So we have a rectangular corral here and a rectangular corral here, and they share a fence on one side here in the middle. So there's 400 meters of fencing available. So if I call this X, then I can call this Y. This here would also be X. So the amount of fencing available is 400 meters. That's got to cover all of the perimeter plus this little fence going down the middle. I'm still going to call it perimeter. So the perimeter that's available is 3x plus 2y, and that's going to equal 400 meters. But the question here is, what dimensions should the rancher use to construct each corral so that together they will enclose the largest possible area? So the area is what we're trying to maximize. So the area, as I've drawn this, is area equals length times width, or x times y. In order to find the maximum or enclose the largest possible area or maximum possible area, we're going to have to find the derivative. However, we've got too many variables. That's why we use this secondary equation here. If I want to get y by itself, I could subtract 3x and then divide by 2. And then I could take this expression for y and plug it in there. So then the area is that. Now if we take the derivative, 2 is going to drop down in front. It's going to cancel with that 2, leaving negative 3x plus 200. Now that's going to equal 0 when x equals 200 divided by 3. Now, when x equals 200 divided by 3, we still need to find y, so we can go back up to this perimeter equation here. If I plug 200 over 3 in for x, 3 times 200 over 3 is 200, because the 3's would cancel. If you subtract 200 from 400, you get 200. So 2y equals 200, which means that y equals 100. Now it says here, what dimensions should the rancher use to construct each corral so that together they will enclose the largest possible area? Y equals 100 means the whole thing here is 100. So each corral is what they're asking. We got to make sure we're specific to answer the question that's being asked. Each corral here is going to be x, or 200 over 3 times 50, because remember the whole length is 100. So it's each corral the dimension is 200 over 3 meters by 50 meters. And before we move on from this one, I made the cardinal sin of a problem like this. I did forget to prove that this value right here, x equals 200 over 3, we need to actually prove it's a maximum. All we've done so far is shown that it's a critical number. There is no proof on here that this is a maximum value. which is what they're asking us to find, the largest possible area. So what you would need to show is that you've done the first derivative test, 200 over 3. So if we tested something like 1 as a test point and 100 as a test point, 1 into the first derivative here, negative 3 times 1 plus 200 is positive. But if we plug 100 in, negative 3 times 100 plus 200 is negative. So the function is increasing and then decreasing, meaning at 200 over 3 we have a maximum value. So that proves that this x value is the maximum value for this function using the first derivative test. And these are the dimensions that would give us the largest possible area. Question 7 is from section 3.5. We have to find the price that will yield a maximum profit here. So remember, profit is equal to revenue minus cost. We have a cost function. What we don't have is revenue. So remember, revenue is equal to x times little p, which little p is given right here. So that's x, and little p stands for price, 36 minus 4x, which is negative 4x squared plus 36x. Excuse me, so this is revenue. So revenue minus cost is going to be this function, subtract this function for profit. So profit equals revenue, negative 4x squared plus 36x, minus cost, which is 2x squared plus 6. So it's negative 6x squared plus 36x minus 6. Now, to find maximum profit, we need the derivative of profit. So that's negative 12x plus 36. I'm going to set that equal to 0. We get x is equal to 3. So producing and selling 3 units would bring us maximum profit, but what they want is what price will yield maximum profit. So number of units, 3, needs to be input into the price function. 4 times 3, well, let's write this down. Little p for price is 36 minus 12 times the number of units that yield the maximum, which is, well, it's not 12, it's 4. 36 minus 4 times 3. So this is 36 minus 12, which is $24. All right, question 8 is from section 3.6. For part A, we just need to find the asymptotes. So we'll start with the vertical asymptote. I'm going to write the denominator in factored form, minus 2 and plus 2. So the vertical asymptotes are x equals 2 and x equals negative 2. Now the horizontal asymptote of a rational function, remember, is found by comparing the degree of the numerator to the degree of the denominator. If they're the same degree, then you divide leading coefficients. If the numerator is smaller than the denominator in terms of degree, then the horizontal asymptote is 0, which is the case here. So the horizontal asymptote is y equals 0. Now for part B, the limit as x approaches infinity, this is a limit at infinity. As x approaches infinity is a description of end behavior of a graph. What is the end behavior as x approaches infinity? for rational functions, that is what the horizontal asymptote does, is describes the end behavior as x either approaches infinity or negative infinity. So the limit as x approaches infinity of a rational function really is just another way of asking where is the horizontal asymptote, if there is one. So the horizontal asymptote of this function is y equals 0. So as x approaches infinity, y approaches 0. So that's equal to 0. Now, for part C, the limit as x approaches -2 from the positive. -2, remember, is one of the vertical asymptotes. So there were a few ways in discussion and in your notes we talked about evaluating this infinite limit is what it's called. One of the ways is to look at the graph, which we're going to do in the next problem. So I'm going to skip. Okay, I'm going to head to number 9, and we're going to graph this function, and then we'll go back and answer question 8c. So the vertical asymptotes were 2 and -2, and we had a horizontal asymptote at y equals 0. It was x minus 1 over x minus 2 times x plus 2. The other thing we need on here are the intercepts. So the x-intercept is when y equals 0. So if we had 0 equals, a rational function is only going to equal 0 when the numerator is equal to 0. The value that makes the numerator equal 0 is a 1. So the x-intercept is the point 1 comma 0. The y-intercept is found by letting x equal 0. So if x equals 0, we have -1 in the numerator, and then -2 times +2 is -4. So we have -1 divided by -4, which is 1/4. So if we zoom in there, these 2 points are connected like that. Now, right here with this part of the graph, as it is approaching this vertical asymptote, it's either going to tend upward towards positive infinity or it's going to turn down towards negative infinity. It can't turn down, it's already above the x-axis. It can't turn around and come back down because there is not a 0 or an x-intercept right here. So it's got to continue upward toward positive infinity. Now this is exactly what part 8 part C was asking. What's the limit as x approaches -2 from the positive side? So this is from the positive side and we're approaching -2 and we're going up to positive infinity. Completing the graph, over here on the right side of this graph, we are either going to have a piece of the graph up here or a piece of the graph down here. So one way we can do this is just by testing a point like x equals 3 and figuring out if it's above the x-axis or below the x-axis. So when x equals 3, 3 minus 1 is 2, 3 minus 2 is 1, 3 plus 2 is 5, 1 times 5 is 5, 2 divided by 5 is 2/5. So 3 comma 2/5 is right about here. And we could do the same thing over here. We could test -3. -3 minus 1 is -4. -3 minus 2 is -5. -3 plus 2 is -1. -5 times -1 is 5. Here we have -4/5. So that's right about there. Okay, question 10. We need to answer a bunch of questions here. Determine the intervals in which the function is increasing, decreasing, and find all relative extrema. So for that, we need the first derivative test. So we're going to set that equal to 0. The critical numbers there are going to be 0 and 4. And then we need test point. I'm going to do -1, +1, and +5. So when I plug -1, we have -1 multiplied by -5, which is +5, so positive. For test 1, we have 1 times 1 minus 4, that's -3. 1 times -3 is -3, or negative. We test 5. 5 times 5 minus 4 is 5 times 1, which is positive. So we have an increasing interval from -infinity to 0 and from 4 to infinity, and a decreasing interval from 0 to 4. So it's increasing from -infinity to 0 and 4 to infinity, and it decreases between 0 and 4. And also, since it switches from increasing to decreasing, we have a relative max at x equals 0. So there's a relative max at the point where x equals 0, and then to figure out the y value, remember we plug in 0 into the original function, and we get 0 minus 0, which is 0. Now here we have a decreasing to increasing, which means at x equals 4, there's a relative min at the point 4, and then we can plug 4 in for x. This is the general form. I've also provided the factored form, which is going to help us when we have to graph to find the zeros, but you can plug 4 into either form here. So 4 squared is 16. 16 over 3 is 16/3. Here we have 4 minus 6, which is -2. So we have 16/3 times -2, which is -32/3. Okay. All right, now the concavity is the second derivative. So that's going to be 2x minus 4. If we set that equal to 0, we get x equals 2. So if we do a test point of 1 and a test point of 3, in the second derivative, 2 minus 4 is negative. But 3 is going to give us 2 times 3 at 6. 6 minus 4 is 2, positive 2. So we have concave down and concave up. So it's concave down from -infinity to 2. Concave up is from 2 to infinity. The inflection point occurs because we're switching concavity, so the inflection point is when x is equal to 2. If we come back up to the original function and plug in x equals 2, we're going to have 2 squared is 4. 4 times 1/3 is 4/3. 2 minus 6 is -4, so 4/3 times -4 is -16/3. Now we sketch the graph of the function rather. So we have increased, decreasing intervals, the maximum values. If we have an inflection point, what we're missing are the intercepts. Okay, so the intercepts are found going back to the original function in factored form. Here we're going to have an intercept at 6, an x-intercept at x equals 6 and at x equals 0. So x-intercept when x equals 0 and when x equals 6. And this point 0, 0, which was one of our relative max values, also counts as our y-intercept. So those are intercepts. Now we put on the relative extrema, so we have 0, 0 and 4, comma, negative 32 thirds. So negative 32 thirds is negative 10, right around negative 10 point something. So it's pretty much 4 comma negative 10. So 4 comma negative 10, we write it here. This is 4 comma negative 32 thirds. That's our minimum value. Is our maximum value. The inflection point is 2 comma negative 16 thirds. So 16 thirds, that's a little lower than negative 5. So 2 comma 16 thirds. It's right there. That's the inflection point. Now we're increasing from negative infinity to 0. So that's increasing, and then we start to decrease from 0 to 4. So we decrease from 0 to 4, and then we increase again from 4 to infinity. And let's check here. We should be concave down here from negative infinity to 2, but then from 2 to infinity we're concave up. Well, it looks like we have everything 6 comma 0, 0 comma 0, everything's labeled. And that's the graph.